My name is Steve Hoover. I'm the founder of a startup called Redwood EDA. And I'm going to be talking today about a design methodology called Transaction Level Verilog and the ecosystem around that design methodology and language. I'll start with a quick demo of the Makerchip platform. This is a platform that's offered by Redwood EDA, a free platform for developing, and it has support for Transaction Level Verilog. After demoing Makerchip, I'll talk about the role that abstraction plays in the design process. And after that, you'll get a chance to do some playing around with Makerchip yourselves. So you'll start out with combinational logic, a very simple combinational logic circuit, then a very simple sequential logic circuit, and then most likely this will just be presentation style. I think we'll probably run out of time to do a hands-on exercise with pipelines. And then I'll wrap things up, giving some general perspective on other things going on with transaction level Verilog. So first, a quick demo of the Makerchip platform. So I'm in Makerchip here. Makerchip gives you an editor. So this is online. Just go to makerchip.com. Editor to work with your design. It gives you a log, and we can organize our session a little bit better so you can see any errors and whatnot. Errors also show up in this nav TLV tab, which is also representing your source code. This is how the tool interprets your source code. And this version of the source code is useful for debug. So here I've highlighted a signal in my model. I also have a block diagram here, and that signal that I selected is highlighted in this diagram. And I can see the expression for that signal. I also get a waveform viewer. So as I'm debugging my design, if I see something that looks suspicious about a particular signal, let's say something looks wrong here with this dest signal, I can also highlight that in my waveform viewer. And again, it will highlight in the logic diagram so I can understand my circuit. And it will also highlight here in the code. In addition to this, a more recent feature of Makerchip is this Viz tab. And this Viz tab enables a logic designer to create a custom visualization of their circuit behavior. So this is a new way to do circuit design. While you're developing your hardware logic, you can simultaneously develop visualization logic inline in the same source code that expresses how you want to visualize your circuit behavior. So in this Viz Alpha section, I have JavaScript code that is expressing how I want the visualization to look based on the signals in my circuit. So your Viz code has access to all the data from your waveform, and it can use that data to express your circuit in a more meaningful way. So the circuit that we're looking at here is a very simple ring network. And if I step the simulation and visualization, you can see that this ring is passing data from one port to an output port. And we can step and see those pieces of data moving through the ring network. All right, so back to our presentation. So first I want to give some general perspective on the importance of better design methodology. We've been using RTL Design Methodology since about 1985. This was the time of the i386 processor. And I want you to just think about the clock speeds that we were designing with and the transistor counts that we were designing with in 1985. I know most of you probably weren't alive in 1985, but just try to think about it. We all understand the scaling of technology, but thinking back this far, it's kind of eye-opening. So in 1985, the 386 processor had a clock that ran at 33 megahertz. Today, or the slide's actually a bit dated, so not even today. And I apologize, I'm not leaving enough time for Russian translation here. So in 2017, AMD EPYC came out with a clock speed of 3.2 gigahertz. So this is 100 times faster. The clock is running at 100 times the frequency. That means in a single clock pulse in 1985, we have 100 clock pulses in 2017, right? It's hard to imagine the clock running that much faster. Transistor counts. Think about what you think the delta is between 1985 and 2017. Was anybody thinking 70,000x? Right, so think about these numbers. In 1985, we fit 275,000 transistors. That means probably about 70,000 logic gates, in fact. So in 2017, we can fit 70,000 CPU cores. All right, and that's, of course, assuming that all you're doing is stamping out the cores with no interconnect. And there's some other scaling factors to consider and whatnot. But, you know, to a first order, you look at these numbers, and what they're telling you is that if our basic building block in 1985 was a logic gate, our basic building block now is a CPU core. All right? Design methodology is fundamentally has to be different, right? The game has changed completely. And so that's the, you know, at a high level, the motivation for the need for better design methodology. I was a circuit designer for 18 years before starting Redwood EDA. And, you know, I know firsthand how painful it is to try to design circuitry at the scale of today's designs using an RTL methodology. And that was really the motivation for me to make a shift in my career. All right, so the key to better design methodology is how we manage abstraction. Right, so register transfer level design for most folks serves as the golden reference model. And this golden reference model is the target of our verification effort. Below the register transfer level, gate level, device level, those are generally constructed by tools, automated tools from the register transfer level logic. So for the most part, the RTL is the lowest level that we deal with. We also create higher level models, say transaction level or behavioral specifications that help in the early stages of the design process and help with verification. With transaction level design, we elevate the specification of behavior to the transaction level. Hardware design, though, is fundamentally different from software design. All right, and abstraction, as a result, is more challenging to deal with. In software, if you have some slow code, that slow code affects the execution of that code only. In a hardware circuit, if you have a slow logic path, that slow logic path can limit your cycle time. Okay, your cycle time for your circuit is set by the worst path in your hardware. In other words, every path in your hardware has to meet the clock cycle time. And that makes hardware design fundamentally more difficult than software. And with hardware, you have to have lower level control over the implementation of your behavior. So the philosophy of transaction level Verilog is that we have a behavioral model at the transaction level, and we have mechanisms to specify the implementation of that behavior at the register transfer level. This allows us to focus our verification energy at a higher level of abstraction, but still have control of the design at the register transfer level when we need to have that level of control to get the quality of results that we're after. So expanding on this picture a bit, the higher level models. This is a typical RTL design methodology. You've got your RTL model, that's your verification focus. And you've got various higher level models above that. So memory models, an instruction set architecture model, protocol model, verification models for transactors, checkers, coverage, assertions, visualization, and some things off to the side that are more loosely coupled with the RTL. With transaction level design, your verification focuses at a higher level of abstraction. You're able to map to the register transfer level detail. But this transaction level model is now closer to your other models in abstraction. And that's very important. There's a lot of code actually that's connecting these higher level models to your register transfer level model in a register transfer level methodology. Now this code is all simpler, and more importantly, a lot of the change that takes place in a register transfer level model to achieve the implementation that you need, a lot of that change gets absorbed in these mappings, which now have no impact on the verification effort. The transaction level model stays stable. And also from this one transaction level model, you can have different implementations that retain the same transaction level behavioral specification. All right, so now is your chance to get your feet wet with Makerchip. This slide here is pretty self-explanatory. So I'm going to be quiet actually and let you go through these slides. I apologize for the typo here. This is just makerchip.com. So the exercise here is essentially just to become familiar with the platform. And basically, if you're able to reproduce what's showing on the screen here within makerchip.com, you've finished this exercise. So just walk through these steps to become familiar with Makerchip yourself. And I'll sit back and be quiet for 2 minutes. All right, 30 seconds more or so. All right, so hopefully everybody is finishing up. Just a few more seconds. And I'll just quickly walk through this myself as well, in case anybody had trouble. Okay, so the validity tutorial. The example. Organize your screen. Highlight signals. All right. Okay. So next, we'll do a quick exercise with about as simple a circuit as you can make. So you'll create an inverter. And again, the instructions here are pretty self-explanatory. So I'll let you go through them at your own pace. And I'll give you about 2 or 3 minutes to go through these. All right, so again, I'll walk through this as well. So I'm going to start with the default template, which you can actually find here. Equals in, and compile that. I compiled with Control Enter as a shortcut. And you can see down here in the waveform that I have a circuit, and I forgot the inversion, so I'm getting out equals in. And yeah, I think that was basically the exercise, and then you can do other logic like in and into. And you can see again the AND functionality. Where the output is only asserted if both inputs are asserted. Okay, so back to the presentation. Let's see, I'm trying to think if we need this exercise. I think we can. Let's skip vectors, but this is just, I'll just quickly talk through this, and feel free to try it as well as I'm talking, but I'm not going to spend any time on it. So here we're just doing an addition instead of a basic logic gate, and for that we would need to provide bit ranges on the operations, because these are multiple bit operations. All right, for the next example, we're going to do a simple sequential logic circuit. We're going to implement a circuit that's computing the Fibonacci series. So you're probably familiar with the Fibonacci series. This is where every number in the series is the sum of the previous two numbers in the series. We start off with two ones. So 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, etc. And to implement this in hardware, we're using, so first of all, we need an adder to sum the previous two values. And we need the previous two values. So if num is the current value, right, each cycle of simulation, each cycle of the clock, we're going to compute the next number in the sequence. And we do that from the previous two numbers, so we need those two values. And we're going to hold on to the previous value and the previous value by using flip-flops, which are represented like this. And the little triangle here is representing that these flip-flops are controlled by a clock. We're not actually drawing the clock feeding in, but that's implied by these triangles and the icon for the flop. All right, and this results in a waveform that contains the Fibonacci sequence or series. So we have 2 1s, 2 3 5 8. There's something missing, however, from this circuit. Any ideas what's missing? So we have nothing to initialize the circuit. The circuit needs a reset. And that's kind of the hallmark of sequential logic. So sequential logic will have both a clock to sequence the logic and also a reset to initialize that logic. So here I'm adding in the reset to the circuit. The reset can go directly into the flip-flop. Here I'm showing it a little bit more explicitly, controlling what we assign that flip-flop to. So when we reset the circuit, we're going to use that reset period. So reset is going to assert for a long period of time and then deassert for the circuit to operate. Often you'll see a negatively asserted reset. Here I'm just using reset positively asserted. So to initialize our sequence of ones during reset, we're going to select a 1 value to populate this flip-flop. And the clock is running during reset, so that 1 will propagate through. We're selecting the 1 propagates, our circuit is, these flip-flops are loaded with 1s. And then after reset, we're selecting the sum of the previous values, and we begin computing our sequence. And this, in TL-Verilog, is the expression of this logic. So we have a number, and we're making that number a 32-bit number. And that number, if reset, is 1. And here I'm using a ternary operator. So the ternary operator is this question mark colon. And you're probably familiar with this, if not from Verilog, from C or JavaScript, etc. So this ternary operator is going to select 1 if reset. Otherwise, it's going to select this expression. And this expression is the sum of the previous value and the previous value. Now, if we were doing this in RTL, we would explicitly have a flip-flop, this flip-flop, this flip-flop. We would explicitly have signal declarations, not only for num, but also for the previous version of num and the previous version of num. In TL-Verilog, we need none of those things. We assign num, that acts as the declaration, and we immediately have access to previous as far back as we want to go by using this ahead by operator. Ahead by 1, ahead by 2. Okay, so this is the complete TL-Verilog expression of this circuit. And I'll let you guys code up a similar circuit, slightly simpler, but very similar to the Fibonacci sequence. So I'll let you guys try your hand at coding up this free-running counter circuit. So the free-running counter is going to reset to 0, and then after reset, it's going to begin immediately counting, incrementing by 1. Okay, so I've put this Fibonacci sequence code on the right here for reference. Note that your TL-Verilog code needs to be indented. Every level of indentation is 3 spaces. So your logic expression will be 3 spaces under the TLV mnemonic. All right, so that's the exercise, and I'll give you a chance, 4 or 5 minutes to try to go through this and get a circuit that is incrementing. Okay, a few seconds more. All right, hopefully most of you were able to create an incrementer. I'll quickly do this myself as well. So in place of this expression, we want count. That's going to be 16 bits. And that's going to be on reset, 0. Otherwise, the previous count plus 1. Compile that. And that does indeed give me a counter circuit. All right, so one of the real fundamental aspects of transaction level Verilog is that it uses a timing abstract modeling approach. And timing abstraction is another way to say free-flowing pipeline. Timing abstract modeling takes many forms. So I'll explain what I mean by timing abstract modeling in TL-Verilog context. So I'll explain it by example. This is an example of a circuit that is computing Pythagoras' theorem. So to compute Pythagoras' theorem, we need to square 2 inputs, A and B. We need to add them together, and we need to take the square root. And I've distributed this computation over 3 pipeline stages. meaning I'm putting flip-flops in between, because the computation is too deep to perform in a single cycle. In fact, square root itself is a whole different game that you could never compute in a cycle, but just for illustration purposes, we'll assume that's a single cycle square root. The way to view this circuit in a transaction level mindset is to put this this computation in a pipeline. So we've drawn our three-stage pipeline. We've drawn logic in each stage of the pipeline. You'll notice in this drawing I have taken out the flip-flops. The flip-flops are implied by the fact that we're carrying values from one pipeline stage to the next pipeline stage. In TL-Verilog, you can express this circuit this way. And you can see a very direct correlation between the code and the picture. In comparison, the SystemVerilog, you can code a pipeline many different ways. This is one way of coding this pipeline, following best coding practice in industry. We've got signal declarations for all the various signals involved here. We've got 3 explicit flip-flops, and we have the logic expressions. And you can see in the TL-Verilog primarily is just the logic expressions in appropriate context. And that context, the pipeline stages, implies the signals and the flip-flops. All right, so just a very quick taste of pipelines. The code reduction that you see is a nice thing. It certainly eliminates bugs. The real benefit of timing abstract modeling and pipelines is the ability to safely and easily retime logic within your pipeline. So I won't talk too much about that because our time is running short. So let me just point you at some other resources in case you want to learn more about TL-Verilog. Of course, you know there's tutorials in the Makerchip IDE, so feel free to go through these various tutorials at your own pace. And redwoodeda.com has plenty of other resources. There's more here about TL-Verilog from a commercial perspective. There's visual debug information. I do a lot of work with RISC-V and also with cloud FPGAs. There are really exciting opportunities shaping the future, taking advantage of FPGAs being accessible in the cloud. I also do a lot of training, so there are a lot of resources here. I work with VLSI Design, VLSI System Design, and the Open Source FPGA Foundation. And I'm really excited about this training we have coming up through OSFPGA for working with FPGAs in Makerchip. So within Makerchip, we actually create this virtual FPGA environment where you can design for FPGAs and then export your designs onto physical FPGAs. There's plenty of other resources here. Verification with TL-Verilog is something we didn't really touch on. There's some information here about using TL-Verilog for formal verification in the context of RISC-V. So these 2 videos, and similarly there's a article here verifying RISC-V in 1 page of code. So explore on your own. I hope I've inspired you to do that, and I hope you enjoy the talk and enjoy the rest of ChipEXPO 2021. Thanks.